Today we'll be deriving the magnetic force. So deriving the magnetic force. Now we're given the main equation that F is equal to Q times E, which is the electric field, plus V, which is the velocity of our single point charge, cross B, which is going to be our magnetic field. Now, since we're only concerned about magnetic force for today, we have that F is just equal to Q, which is the charge of our test charge, times V, which is its velocity, cross B, which is once again its magnetic field. Now, this is only for a single charge. A charge, and it has a magnitude of Q, moving at a velocity of V, and within some magnetic field B. Now what happens, let's consider the case if we have a wire. So for a wire, let's say we have a steady current, which is to say I is going to be constant. Now we also have the length of this wire is going to equal to L, and we'll have A equal the area of this wire. Now what we want to find is Q. What is the total Q for our wire in this case? Well, we can consider it to be some kind of density constant times V, which in this case, this V is going to represent the volume. So what we have is that for our density constant, we have that it's going to equal to the number of charges per unit volume. So we have the number of charged particles in that volume times the charge on each particle. And since we know that this is a wire and it has a current, and a current is a steady stream of electrons, so a current is a stream of electrons, we know that each of those electrons is going to have a magnitude, the magnitude of the charge of an electron, which is going to be the same. So we have N times E. And we're going to divide that by the V, because when we have the density constant, it's going to equal to the number of charges per unit volume. And once we multiply that by V, we get that Q equals NE, where N is dimensionless and E has the units of a charge, and we find that unit-wise this checks out. Now, how do we define I, however? Because we ultimately want to relate I to the force, because when we're dealing with wires, we're going to more often know about I than about every single small point charge and their relative velocities. So we have that I is going to be defined as dq over dt, which we can think of as the rate of charge flow over time. Now, knowing what we know about Q, we can say this is really just this, the derivative of rho times V over dt. And since we know that rho here we said is going to be a constant, so we can take it out to get that we get dV over dt. And since we know that it's a wire, what we find really is that the A is going to be constant throughout, or at least in this case we're going to assume that it's going to be constant. So we can also take that out to get rho times A times, and V, we say V is just A times L times dL over dt. Now what is dL over dt? Well, it's distance over time, so it's really just a velocity. It's the velocity of those moving charges. So we have that I is rho times A times V. And in this case, this V is going to be the V of the velocity, not the volume. So we have that I equals this. Well, what happens when we look back at what we have in F and try to figure something out? So we have that F is going to equal to, in this case, I'll call it big Q, because it's not just a single charge, but many charges, times V cross B. And once again, we found that Q here was equal to this expression. So we have that Q is equal to rho times V, and the velocity cross B. So then what we find here is that we can actually find an expression for V. We found that I is equal to rho times A times V. Well, then that implies that V is just going to equal to I divided by rho A. So if we plug that in here, we find that this is Q, and then V we can rewrite as I over rho A cross B, and we find that the rho's cancel out, and the V and A cancel out to get an L, so we have that L times I cross B is going to equal to our magnetic force, and thus we have an expression for our magnetic force for when we have a wire and a constant current that's running through it.